When you're ready, let me know. Okay, so this one is regarding the deviations for gaseous state. Okay, deviations for gaseous state. Okay, there are two deviations basically. There is the negative deviation where the ideal graph for PV over T versus PV over T is equal to NR. So ideally it should be a constant. Okay, so this is a constant. However, in real life, you're going to find it goes down and it comes up. Okay, at the point where it's going down, this is called your negative deviation over here. And when it starts to overwhelm, when the positive deviation starts to overwhelm, this is the other factor, and you find that the graph goes up instead. Okay, the extent of which the negative and positive deviation happens depends on two factors. So now look at the two factors over here. Factor number one, when its negative deviation is due to the intermolecular forces of attraction being significant. This is the second assumption of the kinetic theory of gases that you have. When it's the second assumption that's being violated, then you get negative deviation. This is the first one that you have. Okay? The other one, this is your first assumption. Okay, when the first assumption is being violated, you find that the volumes become significant. Okay, the volume of the particles becomes significant, and as a result of that, okay, you get a positive deviation. This happens when the pressure gets high. Okay, so negative deviation is at low pressures, high IMF. Okay, and over here, IMF is not a constant anymore. This is where it's high pressure, meaning what it does is that the high pressure of the whole gas leads to significant volume. Okay, this is because as the pressure of the particles of the gas, let's say initially the particles are all distributed equally around. Okay, as you increase the pressure, you reduce the volume. The particles are now going to be in a smaller volume. So the percentage space that it takes up is actually now more. Okay, because of that, it becomes a significant volume. Okay, now looking at each one of them in sequence. For negative deviation, the cause is that there's attraction between particles. Okay, these are the IMF, intermolecular forces. Okay, the attraction actually, what it do is that it actually reduces the force that the particles collide the wall with. Okay, so because of in the first case, right, when the particles collide against the wall, wait for that. When the particles collide against the wall, they hit a certain force. When the first particle is going against the wall, a second particle at the back is pulling it back because of intermolecular forces. So imagine if I have just two of these markers. One of them is trying to collide against the wall. Okay, the second one, because it's attracting it backwards, it doesn't now attack with the same force. It's now a weaker force. Because of that, it actually reduces the force that collides the wall. Okay, those who do physics will know that pressure is equal to this force over the area that it collides. So when the force is reduced, the pressure is reduced. And because of that, the pressure overall is reduced. So what you then get, the effect here, is this. The effect is that the pressure, the real pressure, not the fake one, not the ideal one, the real pressure drops because the force has dropped. Okay, the other effect is that now P ideal, write that properly, P of the real times your volume is constant in this first scenario, is less than your P ideal as volume. Okay, P real, your real pressure is less than your ideal pressure. So overall PV is lesser than your PV in ideal case. That is why it goes down. Because the P, this line here is PV for the real one. For the real gas, the PV actually drops because initially your P real drops. P real drops, your P real times V is less than your P ideal times V. That's the first one. In the second scenario here, okay, the cause is because here your particle volume compared to container becomes significant. Okay, say that again now. The particle volume must be compared to something. The particle volumes compared to the whole container now becomes significant. Initially insignificant, now it becomes significant. Another way of looking at it is this. If you look at the assumption itself, the assumption basically says that the particle volume you almost assume as if they are not there. Okay, that means they are like a vacuum. So essentially, when you look at the real gas like this, right, the part of it which is empty, the vacuum, is the ideal part. Okay, so the effect of that, the particle volume now becoming significant, because of that, right, because it becomes significant, now your V ideal gas, okay, like I mentioned, I already explained it, let me explain one more time now. The volume of the ideal gas is the part of the real gas that can still act as ideal. Okay, how is that possible? How can a real gas have parts which are ideal, parts which are not? Okay, so basically we are looking at the vacuum. This is referring to the vacuum. Okay, another way of putting it is the empty spaces between the particles. Okay, so the empty spaces is basically the ideal part. The empty spaces is the part where the particles don't exist, or according to the assumption, is where the volume of the particles is insignificant. Okay, so the final effect is this. This is my effect. The final effect, use a different color. The final effect is this. My V ideal is less than my V real. Because in a gas like this, let's say if I look at this gas, the particles, if I collapse all of them, condense them to one side. Now, this means that the rest of it here, which is vacuum, is less than the whole real volume. So V real, which is the whole thing, this part, the smaller part, okay, is slightly lesser than the whole thing. This part here, the blank part, is the V ideal. Okay, so the V ideal is now lesser than the V real. Okay, effect of this is when I combine this with the pressure, my P stays the same, V ideal is less than my P V real. Another way of saying it, PV of the real gas is greater than the PV of the ideal gas. Going back there, my PV real is greater than my PV ideal. This is a positive deviation. PV real starts to become more than my PV ideal. It goes up. That's where the positive deviation takes over. Okay, so just a quick recap again. Negative deviation arises because of IMF being significant. It grows significant, so it becomes negative. But over time, when you increase more and more pressure, as the pressure increases, your positive deviation becomes more significant. That's because your particle volume becomes significant. And when the particle volume becomes significant, you find that this line here, PV real, it becomes more than PV ideal. So it overwhelms and then you get the shape. Okay, how the different shapes, because you can get this kind of shape as well. This means it's a different gas. If they all cross the same point, it means it's the same gas but different temperature. The same point, different temperature. All these different gases. Different gases cross different point, same gas cross same point. That's all for the deviation.